In this video, we're going to look more closely at the planets and see how their characteristics differ. We'll start with some pretty pictures of the solar system. These are two distinct photographs of Earth and Mars placed next to each other for size comparison, and you can see that Earth is much larger than Mars. These are all scale models of the terrestrial planets and Pluto. You can see Earth kind of dominates the terrestrial planets, although Earth and Venus are nearly twins, and then Mars, Mercury, and Pluto. If we add in the Jovian planets, you can see that they dwarf the terrestrial planets. And it seems like Uranus and Neptune are almost a different class of planets than Jupiter and Saturn. If you bring the Sun into the mix, you can see that it dwarfs all of the planets. So things are different size-wise. Earth is pretty tiny compared to the size of the Sun. It's tiny compared to Jupiter, and Jupiter is tiny compared to the Sun. Let's start with the Jovian planets and look at their characteristics. This includes Jupiter, of course, and Saturn, Uranus, and Neptune. They have large masses and diameters, no surprise there. They're low density. Now, density is something that people struggle to understand. You can imagine holding a 1-cup measuring cup, and if you do that when it's empty, you're actually feeling the weight of just the measuring cup and whatever air is in it. But if you fill that measuring cup with water, you feel a much heavier weight, and it's obvious that the density of water, the amount of mass it has per unit volume, is much greater than that of air. If you imagine picking up a lead fishing weight, it doesn't have to be very big and it feels fairly hefty. You pick up an equal volume of bread and it doesn't feel very heavy at all. Lead is much more dense than bread. Lead is about the most dense thing that you ever run across in everyday life. An average chunk of Saturn is less dense than water. It would float in a bathtub if you could get an average chunk of Saturn. But the reason for the low densities on the Jovian planets is because most of their apparent size is their atmosphere. They have faster rotations. I was able to experience the fast rotation rate of Jupiter during an observing session one time when we were looking through a telescope at it. This is a picture of Jupiter. You can see a black spot on there. That's the shadow of one of the Galilean moons, either Io, Europa, Ganymede, or Callisto. These are the ones Galileo discovered. You can't see the moon because wherever it is, it blends in with the surface of Jupiter. Most of Jupiter's other moons, 80 are known at present, are too small to see a shadow at this magnification. This is a picture of a very unusual comet that was discovered in March 1993 by Carolyn and Eugene Shoemaker and David Levy, and it was known as Shoemaker-Levy 9 because it was the 9th comet the trio had discovered. The comet looks this way because it had broken up into pieces. When astronomers studied the orbit of it, they realized that it was not orbiting the Sun, but was orbiting Jupiter. And this was the first active comet observed to be orbiting a planet, and had probably been captured by Jupiter sometime back in the 1960s or 70s. Further study revealed that the comet's previous close approach of Jupiter, which would have been in July 1992, it had passed close enough to Jupiter that tidal forces from the planet tore the comet apart. And even further study of the orbit showed that on the comet's next close approach to Jupiter, it would not clear the planet. It was going to impact it instead. The comet fragments were predicted to hit the planet in the last half of July 1994. In the summer of 1994, in late July, reports began to circulate on the still new internet that people were able to see the impact sites in telescopes as small as 4 inches. Well, the college had an 8-inch telescope and an 18-inch telescope. So one July night we set them up in the parking lot on the east side of the Math Science building and started looking for the comet impact sites. For a while we couldn't see anything, but it was a nice night and there were other things to aim the telescopes at, so we looked at those for a while. Then someone aimed one of the telescopes back to Jupiter and we heard, "Hey, I think I see one." In the time that we had been out there, one of the impact sites had rotated into view with that rapid rotation of Jupiter. We watched Jupiter through both telescopes for a couple of hours more and saw more and more of the impact sites rotate into view. Jupiter rotates once in only about 10 hours, so we ended up watching about 1/4 of a rotation for Jupiter in just 2.5 hours of viewing or so. By the way, those impact sites are just big bruises in Jupiter's atmosphere where the comet fragments hit Jupiter at high velocity and vaporized in Jupiter's atmosphere. Some of them were as big as a mountain. The Great Red Spot, which you can see in the left of one of the impact sites, is about 30% larger than Earth. So a typical one of those impact sites was roughly the size of North America. Kind of sobering. Besides those faster rotations, they have longer orbital periods, and they're far from the sun. No surprise with that. The farther they are from the sun, the longer they're going to take to orbit. Turns out these are widely spaced as well. And here's a scale drawing showing how widely spaced they happen to be. Notice how on this scale the 4 terrestrial planets are bunched close to the sun, or at least they appear to be. The closest approach between Earth and Mars is still about 34 million miles, and the shortest time a spacecraft from Earth has reached Mars ever is 128 days. And that one got there quickly because it wasn't stopping by, it was just doing a flyby of Mars, so it didn't have to slow down to go into orbit around the planets. Most spacecraft we send to Mars take about 7 months, or over 200 days. But then look at how spread out the 4 Jovian planets are. The distance between Mars and Jupiter is already more than twice the distance from the Sun to Mars. And then you've got a distance about that big again from Jupiter to Saturn, actually more than that. And then from Saturn to Uranus is bigger still, and from Uranus to Neptune it's bigger still. So those Jovian planets are very far apart compared to the terrestrial planets, which on a human scale are actually fairly far apart. The Jovian planets have many moons, and they have rings. Jupiter now has 80 known moons, and Saturn has 83, and each of the Jovian planets has rings as well, although Saturn's are the only ones that are easily visible from Earth. Saturn's rings consist of objects ranging from particles that are microscopic in size to moonlets, which are hundreds of meters across. Jupiter's faint rings were first discovered by the Voyager 1 spacecraft in 1981 when it flew by Jupiter, and so they're not easy to see. Jupiter's rings are mostly dust particles ejected from some of the smaller moons. Uranus has a more complex ring system than Jupiter, but still not much compared to Saturn. And the rings of Uranus and Neptune as well are very dark and don't reflect very much light. We haven't had a spacecraft study them in any detail. The only visit from spacecraft to Uranus and Neptune was a Voyager 2 flyby in 1986 for Uranus and 1989 for Neptune. The next few pictures will be of Saturn's rings. These were all taken by the Cassini spacecraft, which orbited Saturn for several years. I'll mention a little bit later which years they were. Saturn is definitely the most photogenic planet. The rings themselves are beautiful, but they make very intricate patterns on the top of Saturn's clouds as well. There's a small moon orbiting near the ring plane and beautiful shadows of the rings on Saturn. The Cassini spacecraft orbited Saturn from 2004 to 2017, and at the end of its mission, which was originally only planned for 4 years, the spacecraft was deorbited and it burned up in Saturn's atmosphere. And that was done so that there was no chance of some stray microbe that might have survived on the spacecraft contaminating one of Saturn's moons, where there's a possibility of some life growing. Although they did land a spacecraft on Saturn's moon Titan. It was called the Huygens probe, and it managed to send data and photographs back to Earth for about 90 minutes after landing on there. Here's a picture you've seen before in our unit on infrared telescopes. This is a picture of Uranus, and one of the major rings is easily seen in infrared light. The rings are just about impossible to see from Earth in visible light, I should say. You might notice some common names if you're looking at the names of those moons there. If you've taken a Shakespeare class, you might recognize some of them anyway. Most of the moon names are characters in Shakespeare plays, although a few of them, including Ariel and Umbriel in this picture, maybe Miranda, I can't remember, but they have names that are taken from a poem by Alexander Pope. Okay, the Jovian planets also have very deep atmospheres. They're mostly gaseous with no real surface, although there's a sort of smooth transition in them as you descend deeper and deeper into the atmosphere. It makes an almost smooth transition from a denser and denser gas into a liquid. The liquid eventually reaches a density where hydrogen begins to act as a conductor, and the state is believed to be something called liquid metallic hydrogen. This liquid metallic hydrogen, if that's what it is a good conductor, and with the fast rotations there can be currents, electric currents induced in that material, and that's believed to be what produces the strong magnetic fields that the Jovian planets have. We can subdivide the Jovian planets a little bit. They're all nearly entirely hydrogen and helium. Jupiter and Saturn, almost entirely hydrogen and helium, but Uranus and Neptune are considered as ice giants. They have mostly hydrogen and helium, about 3/4 hydrogen, 1/4 helium, but they also have ices. Uranus and Neptune have more of those, or maybe slushes. CH4, which is methane, NH3, ammonia, and H2O, which should be something that's familiar to you. Temperatures out there are cold enough for these things, all of these things, to be in ice form. So let's take a look at the terrestrial planets. For the most part, you can take the characteristics of the Jovian planets and turn them around. But the terrestrial planets include Earth, Venus, Mercury, and Mars. They have small masses and diameters. That's just the opposite of the Jovian planets. They're mostly rocky with high densities. They don't have much in the way of atmosphere. They're mainly rocky parts. They have slower rotations, shorter orbital periods. Well, they're near the sun. They're bound to have shorter orbital periods. And they're closely spaced. I'll bring back that diagram I have with the planets and their spacing on there, and you can see the terrestrial planets are fairly closely bunched near the sun, although it's still 93 million miles from the Earth to the sun, so they're not that closely spaced. And they have few or no moons and no rings. Mercury and Venus do not have moons. Mars has 2, but in a few million years it'll probably be down to one. One of its moons is on a decaying orbit and will eventually either be torn apart by tidal forces or maybe make a ring around Mars for a short time, or it might just impact the planet. The terrestrial planets have thin atmospheres or no atmosphere at all. The thin atmospheres, that's related to the diameter of the planet. The diameter of the Earth is 8,000 miles, roughly, a radius of 4,000 miles, but by the time you get 20 miles above the surface, you're above 99% of the Earth's atmosphere. And things are similar on Venus, even though Venus has a much denser atmosphere than the Earth. It isn't much thicker. By the way, if there is a hell in the solar system, it would be Venus. The temperature on the surface of Venus is hot enough to melt lead. The density is such, atmospheric pressure at the surface is such that if you were there, the pressure on you is about like being more than half a mile underwater. And if you think about how much the pressure on you increases when you just go 10 feet down in a pool, you can feel it on your ears. Then imagine being half a mile underwater, and it's pretty crazy. All right, that's a detailed look at the differences between the Jovian and the terrestrial planets.